Now move to the second part where we will do some examples that you can understand the concept I have explained in this lecture more clearly. So now start with fourth example where you have to find out the neutral axis depth XU. So the question is, assume straight line instead of parabola for stress strain curve of concrete as given below and partial safety factor as 1. So here you can see this diagram that the graph is linear and value of partial safety factor used 1, hence the final value of curve is 0.67 FCK. A rectangular under reinforced concrete section of 300 mm width and 500 mm effective depth is reinforced with 3 bars of grade of Fe415 each of 16 mm diameter and concrete mix is M20. So there are two questions. The depth of neutral axis from compression fiber, the options are here. On the other hand, the depth of neutral axis obtained as per IS 456 differs from depth of neutral axis obtained in question number 1 and options are here. This question is from GATE examination. So this is a very important question and it will clear your a lot of concepts. So first let us take a look on a strategy to solve this question. First you have to make a graph of stress strain profile for parabolic as well as linear curve. Then you have to use equilibrium equation for tension and compression force to find out the neutral axis as per linear curve. Then you have to use the same process again for parabolic curve as per IS 456-2000. Then the subtraction of neutral axis value from parabolic curve to linear curve gives the answer to your question number 2. So for solution, the given value D 500 mm, B 300 mm and the grade of concrete FCJ 20 Newton per mm square, the grade of steel 415 Newton per mm square. We have 3 steel bar of 16 mm dia and the area of steel AST will be 3 into pi by 4 16 square, that is 603.19 mm square. So the first step is draw stress strain curve. Here you can see that is XU the depth of neutral axis and it is strain profile. This is the stress profile according to IS 456-2000. And on the other hand, this is the profile according to the question. So it is the assumed stress profile. Let us say the compressive force in the assumed profile is C1 dash for rectangular area and C2 dash for triangle area. So let me make it smaller so that you can understand it very easily. Let us assume the point at strain profile is A at neutral axis and B at 0.002 and C at extreme compression fiber. If we consider similar triangle, then AB upon AC will be 0.002 upon 0.0035. It will be 4 upon 7. Hence, the value of AB will be 4 by 7 XU. On the other hand, the value of BC will be XU minus 4 by 7 XU, that is 3 by 7 XU. Now the second step, you have to use equilibrium equation to find out the actual depth of neutral axis. Hence, first we have to find out the total compressive force. It will be 0.67 FCK into 3 by 7 XU and depth B. Then the area of triangular compressive stress block, that is 1 by 2 0.67 FCK into 4 by 7 XU into depth B. And the final value will be 0.48 FCK BXU. On the other hand, tensile force will remain same, that is 0.87 FY AST. So the next step is the actual depth of neutral axis, that is the total compressive force will be equal to total tensile force, that is 0.48 FCK BXU is equal to 0.87 FY AST. Here we have to put all these values that is given in question. The value of concrete grade 20 and width 300 into XU. So when you solve this equation, the value of XU is 75.84, that we can use approximate as 76 mm. Hence, the option for first question is A option, that is 76 mm. Now move to second question. So for second question, the third step is we have to use a neutral axis formula as per IS 456-2000, that is XU is equal to 0.87 Fy AST upon 0.36 FCKB, that I have already derived. When you put all the value in this equation, the value of X is 100.82 mm. We can use the round figure 101 mm. And the question is that we have to find out the difference between the depth of neutral axis from IS 456 and assumed triangular that is given in question. So the value is 101 minus 76 mm, that is 25 mm. Hence the option of second question is C, that is 25 mm. Hence I have explained you here in this question how to find out the actual depth of neutral axis. So now move to another important example, the ultimate moment of resistance MU. A reinforced concrete beam of size 400 into 650 mm is made up of M30 grade of concrete and reinforced with. So there are two sections of this question. The first is 6 bar of 25 mm dia, and in second section there are 8 bar of 25 mm dia, and grade of steel in both section is Fe415. So you have to calculate the moment of resistance of beam and also calculate the area of steel for limiting section, and you can assume the effective cover of 50 mm. So to solve this question, the strategy is first find out the actual limiting, then the actual depth of neutral axis XU, assuming as under reinforced section. So the condition is here that when you find out these two values, you have to assume the section as under reinforced section. Then you have to compare it actual limiting with XU to find out the section type, that it is same as we have assumed, that is under reinforced, or it is balanced section or over reinforced section. Then you have to find out the moment of resistance as per section type, and I have already explained you the relation between XU and XU limiting and which type of the formula you have to use. So the solution is case number 1, the 6 bar of 25 mm dia. First we have to note down the given value, the total depth, that is 650 mm, and B 400 mm. Effective cover is given 50 mm, and the effective depth will be 650 minus 50, 600 mm. Grade of concrete is given as M30 and FCK will be 30 Newton per mm square and Fy 415 Newton per mm square. We have given 6 bar of 25 mm, and the area of steel will be 6 into pi by 4 into 25 square, that is 2945.24 mm square. So here we have noted down all the given data. Now the first step is find the actual limiting. I have already explained you this formula XU limiting upon D as 700 upon 1100 plus 0.87 Fy. Here if you put the value of Fy 415 and effective depth 600, the value of XU limiting is 287.46, that is approximate 288 mm. There is another way we can find out the value of XU limiting, that is the table which is given in IS code. Here the value of XU limiting upon D is given according to steel grade we use 415, and the value of XU limiting upon D, that is 0.48, and the final value of XU limiting, that is same 288 mm. So you can use any method to find out the value of XU limiting. The next step is find the actual depth of neutral axis, and I have already told you in strategy that we assume the section as an under reinforced section. So the formula XU is 0.87 Fy AST upon 0.36 FCKB. Now put all the values here. After putting all the value, when you solve this equation, the final value of XU is 246.15 mm. That is less than 288 mm, the value of XU limiting. Hence, the section is under reinforced as we assumed earlier. The next step is find out the moment of resistance Mu using the tension side formula. We use here tension side formula because our section is under reinforced. The formula is 0.87 Fi AST into D minus 0.42 Ht. Here when we put all the values, the value of ultimate moment of resistance is 528.09 kilonewton meter. The value of moment of resistance that we have find out is factored. Now we have to find out the unfactored moment. 528.09 upon 1.5. Here 1.5 is partial safety factor that we use for load. Final value is 352.06 kilonewton meter. Now move to second case where 8 bar of 25 mm dia are given. All the values given here are same except the number of bars. Hence the area of steel will be 8 into pi by 4 into 25 square, that is 3927 mm square. The first step is find the actual limiting, that is same 288 mm. Next is find out the actual depth of neutral axis assuming as a under reinforced section, and the axis will be 328 mm. That is more than 28 mm actual limiting. Hence the section is not under reinforced as we assume. Hence section is over reinforced, hence steel is not yielded. So we have to limit actual depth up to actual limiting. So the next step, to find out the ultimate moment of resistance, we have to use compression side formula because the section is over reinforced and we have to limit the actual depth up to actual limiting. That is 0.36 FCKB actual limiting into D minus 0.42 actual limiting. When you put all the value in this equation, the final value of Mu limiting will be 596 kilonewton meter. And there is another way you can find out the Mu limiting. I have shown you this table that Mu limiting upon FCKBD square value according to grade of steel, that is given in question Fe415. The value of Mu limiting will be 0.138 FCKBD square, and we have already known the value of B and D. So the final value of Mu limiting is approximate 596.16 kilonewton meter. So this is also the factored moment, and the unfactored moment will be 596 upon 1.5, that is 397.33 kilonewton meter. So the next step in question, they ask the area of steel for limiting section. So here we can use the formula of Mu limiting from tension side because we have to find out the area of steel, that is 0.87 Fi AST into lever arm. So AST will be Mu limiting upon 0.87 Fi D minus 0.42 XU limiting. When you put all the values here, solve this equation, the final value of area 3445.9 mm square. There is another way to find out the area of steel, that is I have explained you as a limiting percentage of tensile steel, PT limiting. The formula of PT limiting is 41.61 FCK upon Fy, actual limiting upon D. When you put all the value here, the value of PT limiting is 1.44%. And another formula of PT limiting is 100 into AST limiting upon BD. So here we have already known the value of PT limiting. We can find out the value of AST limiting as 1.44 into 400 into 600 upon 100. That is 3465.6 mm square. Now move to another important example, the ultimate moment of resistance. A reinforced concrete beam of size 350 mm into 500 mm is made up of M200 grade of concrete and reinforced with Fe415 steel. Beam have a duct of rectangular section of size 100 mm into 200 mm, which is symmetrical about the vertical axis of beam section, and center of duct is at a distance of 175 mm from beam section. So compute moment of resistance of balance section and thus area of steel required. Assume effective cover is 50 mm. So to solve this question, the strategy: first find out the value of actual limiting. It will be equal to depth of neutral axis because the section which is given in question is balance section. Next is you have to divide the area above the balanced neutral axis into a smaller area and find out the compressive force of each area separately. Then after finding the total area, then find the ultimate moment from compression side. Using equilibrium equation, find out the area of steel AST. First note down all the given data, that is total depth 500 mm, breadth 350 mm, effective cover 50 mm. That's why the effective depth will be 500 minus 50, 450 mm. Grade of concrete is M220, that's why SCK 20 Newton per mm square and FY 415 Newton per mm square. So the dimension of duct is 100 mm into 200 mm at a distance of 175 mm from upper compression fiber. So the first step, find out the actual limiting. The value of actual limiting upon D, that is 0.48 for 415 steel, and the final value is 215.55 mm. Let the distance, that is 175 mm, is 100 mm plus 75 mm. The value of actual limiting is 215.5 mm. If we draw the stress profile for this section, hence the value of neutral axis will be at a distance 215.5 mm. So as I have told you earlier that we have to divide the area above the compression into three parts. That is part 1, this is part 2 and this is part 3. Part 1 and part 3 are each of with 125 mm, and under the influence of complete compressive stress area over a depth of 215.55 mm. The part 2 is width of 100 mm and depth of, let us assume it h, of 75 mm. So first we have to find out the depth of rectangular portion of compressive stress. This is the complete stress block of compression. So the depth of rectangular portion will be 3 by 7 xc, that is 3 by 7 into 215.5 mm, 92.3 mm. It means that the section 2 is under rectangular area because 75 mm is less than 92.3 mm. So to further solve it, let us assume C1, C2 and C3 are the compressive force on part 1, part 2 and part 3 respectively. Here C1 will be equal to C3, that is 0.36 FCKB actual limiting, and the final value is 193.995 kilonewton. The value of C2 will be 0.45 FCKBH, and 0.45 20 into, here the breadth of second part is 100 and the depth is 75 mm, and the final compressive force is 67.5 kilonewton. Now the second step is find out the moment of resistance from compression side. We have already found out all the compressive force and moment of resistance at balance stage mu C1 plus C3 into lever arm D minus 0.42 actual limiting, that is same as I have explained you. The compressive force C2 into, here the lever arm will be the total effective depth minus h by 2, that is the centroid of upper rectangular area. Hence when you put all the value here, that the value of C1 and C2 is 193.995, the value of actual limiting 215.55 and the h is 75, the half of 75, 37.5 Newton mm. Hence the final value of moment of resistance is 167.314 kilonewton meter. So now find out the area of steel for balance section. Hence the third step here is use the equation of equilibrium to find out the tension force. total compression force will be equal to total tension force, that is C1 plus C2 plus C3 is equal to T. When you put all the value of C1, C2, C3, the total tensile force value is 457.49 kilonewton. And the fourth step is find out the area of reinforced steel AST. And we know that at a balanced stage, the stresses in steel will be equal to 0.87 Fy. Tensile force will be 0.87 Fy AST, that is equal to 457.49 into 10 to the power 3 Newton. And the final value of area of steel, when you put all the values here, it is 1267.07 mm square. So here we have finished all these three examples, and I hope you have understand the concept of limit state method more clearly with these examples. So let me summarize this lecture, what we have covered here. First, I have explained you the assumption of limit state method. The assumption that is very helpful to understand the analysis and design of beam. Then limiting depth of neutral axis, that we can find out using this formula, actual limiting upon D 700 upon 1100 plus 0.87 Fy, or alternatively we can use this table to find out the limiting depth. Then the actual depth of neutral axis, that we find out using the formula x is equal to 0.87 FIST upon 0.36 FCKB. The condition of this formula is that the axis should be less than or equal to actual limiting. Otherwise, we can use strain compatibility to find out the depth of neutral axis. Then ultimate moment of resistance, that we can find out either from compression side or from tension side. Then comparison of XU and XU limiting, and on the basis of this comparison, we have divided the section into three parts: under reinforced, balanced, and over reinforced section. After explaining all these concepts, there are three examples that are very important for you. So if you have any query, please comment below. We will get back to you shortly. Thanks for watching Team Macon Link.